Hi, in this video, we want to take a look at nominal response models. Okay, so uh, this example is taken from Modern Psychometrics with R, and here is a GitHub website to get the code. And nominal response models use latent variables to model categorical responses. All right, so we have some data and from, let's say, like a test. Now, on this test or questionnaire, quiz, whatever, the responses are not ordered. There isn't like a correct, incorrect. There isn't, low, medium, high. There isn't like a scale from 1 to 10 or anything like that. The responses are not ordered. So this could be something like a survey. Okay, well, what we believe is that there is one under the hood latent variable driving the responses of these questions. And what we want to do, we want to use that latent variable to model the responses that we get. Okay. So how do we do that? Okay, so what's going to happen is that we are going to go through and for each level response of the item, we're going to get a distribution for the latent variable. Okay, and then from there, we're going to get a likelihood given a particular value of the latent variable. Okay, well, then so we have a likelihood for each now this is from the density function. For each value that we have for the latent variable, we have a likelihood for each of the possible responses for that particular question. And what we do, we take the level that has the greatest likelihood, and we say that is our modeled value. Okay, and we can rescale these values to give us a probability of each of the different response levels. There are very few assumptions in this. There are no parallel slopes. Each item gets its own discrimination parameter, that is slope in terms of logistic regression. This is a very flexible model. All right, so for this example, let's go ahead and load the data. We're going to use the WillPat dataset from MPsycho or R. So this has a bunch of survey questions that are, rather conservative and liberal, or left and right, depending on how you want to word it, how you look at it. And the first 15 are conservative. The 16 through 46 columns are considered liberal questions, and then the others, the other columns in the data set are covariates. Okay, so first thing I want to do, I want to go ahead and compute princals of the conservative data. So let's go ahead and use the Giphy package to compute princals. So remember, princals are the categorical version of factor analysis. Okay, so, and we're going to take our conservative data, and it's not ordinal, so we say ordinal is false. All right, so now let's go ahead and plot it and see what's going on. All right, so when I do the plot, so component 1 is our first latent variable, and component 2 is our second latent variable. All right, so we can see that component 1, we've got a split going. We've got nationalism, church, patriotism, and obedience on the left, and then we have things like fair trade, capitalism, low taxes, genetically modified foods, private healthcare, private pensions, privatization, nuclear energy are all going in the other direction. So what this does, this leads me to believe that we could further split up the data set into kind of like an authority and obedience collection of conservative columns. And then we can do like conservative, like money, finance columns. And so what I'm going to do, I'm going to say these are like authority and obedience. Over here, these are conservative dealing with money or finance. All right, so what I'm going to do, I'm going to subset the data based off of the princals plot so that we're looking at the money ones. So I'm just taking all the columns that are not nationalism, patriotism, church authority, or obedience. So now I'm going to compute homals of the reduced variables. So here, this is a generalization of princals. Princals really focus more on the scoring of the categories, and homals give us insight into the category associations. So it's a little bit different, but we're getting some juicy information off of it. And so I'm going to compute the HOMOs off of my even further subsetted data. And let's go ahead and plot it. Okay, so when I look at this, you'll notice I've got 0, 0, 0, 0, 0, 0, 0, 0, 0. All of these are in the, like this cloud, all have 0 for their responses. That's kind of interesting. And here from what I can see, they're overlapping quite a bit. I see a lot of 1s, and here I see a lot of 2s. All right, so we can see there's kind of a cloud going on here. So we can see like free market is pretty far out from the others. So free market 0 is relatively far from free market 2, and free market 1 is going to be floating around there. So we can see free, because of this dispersion, we can see free market is like a stronger, like separating more, over the data set. It's giving us more extreme values from it. While this is probably going to be going, free market is probably going along the spectrum of conservative liberal more than other aspects. Now here we can see that genetically modified foods is rather, compared to the others, kind of close together for all three. And so we can interpret that as it's not really as extreme, it's not like a polarizing issue in terms of conservative and liberal. All right, so let's go ahead and compute a nominal response model for the reduced variables. So I'm going to use the MERT package, and I'm going to use its namesake to do the computations. And I'm saying I just want one latent variable, and I'm going to say that I've got nominal data. Okay, so it'll go through, and I'll start doing the calculations, and here we can see that it's run through a bunch of iterations to converge. We can get the output. So after 24 iterations, the log likelihood is -7557, and we've got very small change since the previous iteration. And here we can see the optimizer that was used and the acceleration to do the fitting, and the number of rectangular quadratures, and it has a latent under the hood density of Gaussian. And here we've got 44 parameters. All right, this is important to pay attention to. Remember, whenever I have like a lot of like modeling going on with, or when I have modeling with a lot of parameters, I need to make sure I have a lot of data to correspond. If I don't have very much data to support a large number of parameters, then I'm prone to overfitting. Okay, so if I have a lot of parameters, I need a lot more data. Something you should always do when you're doing model building where you're unsure if I have enough data, you always want to look at the ratio of observations to parameters. And to give yourself a benchmark, look at the ratio of observations to parameters in a linear regression model. And that kind of gives you an idea of how far off I am, potentially if I am overfitting. And here I get information criterions to see how things are going. All right, and we can look at the statistics of the model. So we can see our degrees of freedom, our p-value. This p-value is large, which indicates there is no lack of fit. So that's good. And then we have our root mean squared error average. And then we get a confidence interval on that. All right, so now let's go ahead and look at the item plots of our nominal response model. All right, so how I applied this, how I went through was I took the item plot function from the MERT package and created this special function and iterated it over all of the individual items in the MERT model that we made previously, our nominal response model. So for each item in MERT model, I went through and I plotted the distributions. And I used the lapply function to iterate over all of them very quickly, very efficiently. So now let's go ahead and take a look at what we've got. And so here we can see that approve is in the blue. And then, or sorry, disapprove is in the blue. Approve is like the purple pink. And I don't know is the green. And down here, this is our latent variable. And so if I look through this, on this data set, we can see that approve is largest for this portion of the distribution of latent variable. I'll know is now the largest. So you'll notice that disapprove is never the most likely of the three possible responses, regardless of what the person's latent variable value is. So around here, we can see that it's probably, disapprove is probably the largest proportionately that ever gets on this individual item on capitalism, but it's never the largest one. So if I was to do like a prediction, if I knew someone's latent variable and I dropped into this model, we would either say that they approve or they don't know. Let's look at privatization. Privatization gives a similar story that the most likely is either approve or don't know. Free market is the same way. Well, look at the variance on that distribution. Something that's interesting about the lower taxes data is that lower taxes really doesn't go along with conservative or liberal. Now, the conservatives are stronger on this data set for this, but it's, you know, there's plenty of the people who are otherwise scoring liberal that want lower taxes. Now, free trade, similar story. Either the most likely is either approve or I don't know. Private healthcare, same. Nuclear energy, similar story. Private pensions. So now here you can see a lot more people do not know. Small government. Now genetically modified foods, this is interesting because it's different from everything else. We can see that it's approve is most common here. Then in this region, we can see it's disapprove, and then it's I don't know. So it's kind of interesting that you know, approve and disapprove are actually adjacent to each other. That in this region it switches, and the I don't know is not like manifesting in the middle. It's kind of interesting. Consumer culture, similar story as the other ones. All right. Well, I hope this has been informative. This is all I've got for you. Take care and goodbye.